Okay, so I'm going to go through our work from Monday, where we had a practice quiz that is similar to what I'm going to be expecting you to be able to do on Thursday and Friday in class. And the setup for the problem is that we have a projectile launcher that's set on a surface so that the projectile is 3 meters above the ground. We've previously measured the speed of the projectile launcher. We'll talk about that in a second at 5 meters per second. The launcher is set to a 25-degree angle. And what we want is to set a hoop a half a meter away so that the projectile goes through the hoop. And then we have a bucket that's 0.3 meters tall, and we want the projectile to go into the bucket. This is the same setup as the lab. And much like the lab, we have the same set of information that we can feel confident about. It's reasonable to think that we can accurately measure the initial vertical position of the projectile. 3 meters is probably pretty darn close. If we wanted to just make a really careful measurement, we could. And so we can assume that that is going to be done. Same for the height of the bucket. That is a measurement that we could make really precisely with a decent ruler. And same for the distance between the launcher and the hoop. So we can assume that the 3 meters, the 0.5 meters, and the 0.3 meters are accurate numbers. And the other number that's probably pretty accurate is the angle of the launcher. We know how to measure angles pretty well. We use protractors or we use plumb lines like our launcher in the classroom. So we can assume that the 25-degree angle is correct as well. What's not probably accurate is the 5 meters per second. And what I asked you to imagine in class when I presented this practice quiz was that we had made the prediction of, or we'd made the measurement of the speed of the launcher using tracker. And when we did that for real, using our real launcher, you all were getting numbers that varied from anywhere from 2 to 3 meters per second. That's a huge range in terms of the percentage, right? That's like a 50% range. So we don't know about the speed, and we don't know about the vertical or horizontal accelerations because we know there's air resistance. So if we solve this problem, we're going to start by making the drawing, which has already been done, and then we'll establish a 0, 0 position, which you can see I've put just below the launcher, and our positive directions in the axes. We have one vector quantity that we need to break into components. And so I'm going to draw my picture. That vector quantity has a magnitude of 5 meters per second. The angle is 25 degrees. I'm putting that into the vector solver, and you can't see that, but that will tell me the horizontal and the vertical parts of that speed. And in this case, that ends up being in the horizontal direction, it's 4.53 meters per second, and in the vertical direction, it's 2.11. So that's about 4.5 at about 2.1. So at this point, we can start listing our variables to solve the problem. And what we'll do is start with the hoop. So with the hoop, we know that it starts horizontally at location 0, and it travels 0.5 meters to the right. So that means its final horizontal position is 0.5 meters. And we used the solver to determine the initial speed, and that is about 4.5 meters per second horizontally in the x direction. And because we're assuming there's no acceleration for now, that means that its final speed is also 4.5 meters per second. And we don't know how long it takes for the ball to move that horizontal distance, but we're going to find that out shortly. In the y dimension, we know the initial position of the projectile. It starts at 3 meters off the ground. And we don't know how high we're going to place our hoop so that's an unknown. Our initial speed vertically, it's traveling about 2.1 meters per second up. It's not going to stay at that same speed. So our final vertical velocity is unknown. And the acceleration is, we're going to assume negative 10 meters per second squared. And we don't know how long it's going to take. So I have enough information using my x variables to find how long it takes to travel that distance. We know its speed, we know the distance it travels, so we can put it into the kinematic solver. And I'm going to just put those numbers into the solver, and then I'm choosing to find time by using the first equation, and I get about 0.11 seconds. That's also how long it's been moving in the y dimension. And so that means that now that we know how long it was moving in the x dimension, we can now use that information to predict where it will be vertically after that amount of time. So I can put into the kinematic solver my starting position of 3, my initial vertical speed of 2.1, my acceleration of negative 10, my time of 0.11, and I get a final position of 3.17 meters. So that's how high I'm going to put the center of my hoop. To find where I put the bucket, a bunch of these values stay the same, not all of them. We no longer know the final horizontal position or the final vertical velocity. We don't know how long it's going to be moving. But we do know where it ends up vertically. We know its final vertical position. It's the height of the bucket. So our final vertical position is going to be, it's going to be 0.3 meters. So I can put all that information into the solver and solve for time. And it will tell me how long it takes to go from 3 meters all the way down to 0.3 meters in the vertical direction. And that ends up being about 0.97 seconds or so. So that means that's how long it's been moving horizontally. And I can now figure out how far it will move horizontally by using the kinematic solver again. So I'm going to put my x variables in of 0, an unknown final position, constant velocity of 4.5 meters per second, an acceleration of 0, and the time of 0.97 seconds. And that gives me a predicted final position of about 4.37 meters. So that's where I'm going to put the bucket. So that's the first part of the problem. In the second part of the problem, we have to make some revisions. We know that if all of our initial parameters are correct, that the path of the ball should be as we predicted. But in the practice quiz, we did a test launch and it didn't quite work. It went through the hoop, but it went through the hoop higher than we thought it would. And it didn't make it all the way to the bucket. And my apologies for the terrible scale of this drawing. That doesn't look like a parabolic arc at all, but that's because my distances are messed up horizontally. So the actual path is a little higher, but a little shorter. And as we mentioned before, we fairly certain about most of our measurements, but what we don't know for sure is our initial velocity really 5 meters per second? Maybe it's a little bigger, maybe it's a little smaller. And is our acceleration really 0 in the horizontal dimension? Maybe it's slowing down a little bit horizontally as it moves. And is our vertical acceleration really free fall, negative 10 meters per second squared? Maybe it's a little bit less than that because of air resistance. And the problem we have here is that if we just monkey around with the initial speed, we can only change it in 2 directions. We can make it bigger or we can make it smaller. If we make it bigger, then we could anticipate that the projectile will go higher, and so that would be good. But if we make it smaller, then what we're going to find is that it doesn't quite reach the bucket, which is also what we saw with the actual launch. So what that means is that we can't just change the initial speed. If we make it bigger, we'll overshoot the bucket. If we make it smaller, we'll undershoot the hoop. So we have to make a slightly different change. And what we're going to do for that is maybe assume a slightly higher speed. That'll get it higher up in the hoop, but a we'll give it a little bit of horizontal acceleration to cause it to slow down, which also kind of makes sense because there's air resistance. So I'm just pulling two numbers out of thin air: 5.2 meters per second and negative zero point 0.8 meters per second squared. Those will be my new values for the initial speed and the horizontal acceleration. We still don't know if those are right, but I think those are going to more closely match the actual path of the projectile. So we'll see how that turns out. The first thing I need to do is adjust my components. And so when I put my new speed into the vector solver, I get a horizontal speed of 4.7 initially and a vertical speed of 2.2. So let's go back through it again and see whether our new projected path is closer to what we actually saw in this theoretical launch. It still goes the same distance horizontally. I now have a initial speed of 4.7. My final speed's not 4.7. I don't actually know that because it's slowing down. It is slowing down at about 0.8 meters per second squared. And so let's see how long it takes to travel that half meter with an initial speed of 4.7 meters per second and an acceleration of negative zero point 0.8 meters per second squared. Put that into the solver, and we get a time that's pretty close to the same time that we got last time. Our new time is, hold tight, typing in my numbers, doing my calculations, and let's see, we're going to get same, about 0.11 second. So that's how long it's moving vertically as well. And then with our new vertical starting speed of 2.2 meters per second, we can put that information into the solver. And what we find is that it will end up at about 3. So it ends up going a little bit higher, not terribly. So it ends up going about 3.18 meters. So that's higher. It's not dramatically higher, but it does match our actual launch a little bit better than our original prediction. Maybe that's enough. We didn't actually measure it in the practice quiz because there wasn't a real launcher. Now let's take a look at whether or not our revised information will correctly predict a shorter trajectory or a shorter range for our projectile. So we're going to, again, erase the things that aren't the same, but we're now going to launch to the top of the bucket, which is 0.3 meters. And we'll put the vertical information into the solver. So our initial position is 3, final position is 0.3. Our initial speed is 2.2. The acceleration is negative 10. And we'll solve for time using the first equation. And what we get is it's about the same, 0.99 seconds. So that's how long it was moving horizontally. And then if we put that time in with our horizontal values of initial position 0, we're now solving for the final position, so that's unknown. Initial velocity is 4.7. The horizontal acceleration is negative 8. and the time is 0.99 seconds. And we get a new horizontal prediction of 4.26 meters. So it does end up more closely matching the actual path taken by the projectile. So that is what I'm going to expect you all to be able to do on the quiz on Thursday and Friday, is make an initial prediction, then revise some parameters, the initial velocity and the accelerations based on data that you get from a test launch, and then test your new values to see if they more closely match the actual launch that you saw when you tested it.